On a late autumn day in 1939, as the European War unfolded and the Pacific simmered with passing tensions, a quieter but no less consequential debate took place inside American air power circles. What shape would strategic bombing take in the coming contest across the vastness of the Pacific? For the United States Army Air Corps, soon to become the Army Air Forces, the answer would have to accept a geography that rendered short-range designs useless. Distances in the Pacific were an order of magnitude greater than those in Europe. Islands separated by hundreds, then thousands of miles of open water. No friendly airfields within easy reach. The enemy capital, Japan, situated beyond the comfortable reach of early U.S. bombers. The problem was not merely one of power or payload. It was a problem of endurance, of fuel, of range, of an aircraft that could fly for hours across the ocean, deliver a crippling blow, and return. In December 1939, visionary planners in Washington sketched the outlines of what they wanted. A heavy bomber with intercontinental range from Pacific bases, adequate payload to threaten industrial targets in the Japanese home islands, and enough defensive armament to survive long flights over hostile seas. The specifications were audacious, perhaps deliberately so. They demanded the kind of performance that would stretch fabrication techniques and engine technology to their limits. Above all, they required an airplane that could operate at high altitude for long durations, carrying both fuel and a strategic bomb load. When the Army issued the formal requirements, a few companies responded. Boeing, then a major builder of transport and medium bombers, proposed what would become the B-29, a large, four-engine, pressurized, long-range bomber built around the concept of sustained high-altitude strategic bombing. The logic behind the requirement was simple and brutal. If the United States was to bring the war to Japan from its Pacific staging areas, the Marianas, later Okinawa, aircraft needed to bridge thousands of miles. Surface fleets and carriers could do much, but the bomber offered something different: the ability to strike industrial centers far inland from a standoff distance, to disrupt war production, and to attack key nodes of transportation and supply without the need to land. High altitude promised protection from light anti-aircraft artillery and the possibility of operating above much fighter opposition, at least in the planners' assessments of 1939 and 1940. But to achieve this required pushing technology forward: stronger airframes, greater fuel capacity, new engines, and innovations for crew protection and comfort on multi-hour missions. Boeing's design would attempt to combine all these in one airframe. The man most often associated with the B-29 project inside the Boeing engineering offices was Claremont E. Beaulieu. Not a household name today, but one of a generation of engineers who moved between commercial transport design and the new demands of strategic military aircraft. The chief engineers team at Boeing in Seattle conceived the B-29 as more than a bigger B-17. It was to be a new class. Among the features that marked the B-29's ambition, a pressurized fuselage allowing crew relief from the relentless fatigue of long, high-altitude missions, remotely controlled gun turrets operated by analog computing sites, extensive use of advanced alloys to save weight, and the inclusion of the most powerful radial engines available, the Wright R-3350 duplex Cyclone.
From the outset, the B-29 was a compromise between vision and vulnerability. Pressurization would permit crews to function at altitudes above 30,000 feet without bulky oxygen equipment, a decisive advantage in theory. Remote turrets promised better aerodynamic lines and reduced drag compared with binocular walk-around gun emplacements. But these innovations carried risks. Pressurization required a stronger, heavier fuselage with new seals and bulkhead techniques. Remote turrets required electrical and mechanical systems that had not been proven at scale in combat conditions. And the R-3350 engines, while state-of-the-art in horsepower, were temperamental and thirsty at the levels of continuous power that long Pacific flights demanded. By mid-1941, Boeing had a prototype and the Army Air Forces had a contract. The timing, however, intersected with events that would explode the program into urgent development. The attack on Pearl Harbor on December 7, 1941, reframed the stakes. The U.S. presence in the Pacific had been badly clipped. The need to strike back across oceanic space became a strategic imperative. The B-29 program moved from conceptual ambition to wartime urgency. Government funding surged, production lines expanded, and design sacrifices began to be negotiated not in boardrooms, but under the pressure of calendar dates and battlefield losses. Those decisions were not purely technical. They were also cultural and institutional. The Army Air Forces, under the energetic leadership of General Henry H. Hap Arnold, wanted a bomber that could command the strategic stage. Arnold championed the B-29 as a tool of long-range precision bombing that could break an enemy's will by striking where it hurt: industry, transport, and morale. For Boeing and its subcontractors, the challenge was to translate Arnold's strategic intent into rivets, sheet metal, and machinery, all while wartime priorities pulled production resources toward fighters, transports, and naval construction. The procurement system looked to scale, tens, then hundreds, then thousands of aircraft. But at the beginning, the B-29 remained a delicate balance between the lofty demands of strategy and the practical realities of engineering. One of the central problems was fuel. To meet the range requirement, the B-29 needed enormous tanks. Each gallon of aviation fuel weighed nearly as much as a rifleman. For every kilogram allocated to fuel, something else had to be shaved: armor, redundant systems, or simply payload. The B-29 designers chose to maximize fuel so that the bomber could reach targets across the Pacific while carrying meaningful bomb loads. The immediate consequence was an aircraft heavy at takeoff and sensitive to weight distribution. That sensitivity would ripple through maintenance cycles, deck handling, and the lives of crew who had to operate under strenuous conditions for 10+ hours on mission. Engine choice further defined the airplane's destiny. The R-3350 was a twin-row, 18-cylinder radial engine producing, in later variants, upwards of 2,200 horsepower. On paper, its power-to-weight ratio made it ideal for a large, heavy bomber. In practice, the R-3350 had not been tested in long-duration, continuous power applications of the sort the B-29 demanded. Cooling proved a particular issue. The engine's tight cowling, necessary for aerodynamic efficiency, reduced airflow in some operating regimes. When flown at sustained high power during long climbs or evasive maneuvers, the R-3350s tended to run hot. The combination of high temperatures, high oil pressures, and variable fuel quality from wartime rationing and supply chain variation produced conditions conducive to engine fires.
Engine fires are more than a technical annoyance. They translate directly into combat survivability. An engine fire in a multi-engine bomber can quickly escalate. Fuel lines, hydraulic lines, and control cables run near engines. Heat breeds structural failure. Smoke and flames disorient a crew already operating at the edge of endurance. In the B-29, stories of engines catching and the desperate work to fight them while keeping the massive aircraft aloft entered the lore of crew rooms. The engines, in short, were both the source of the B-29's exceptional capability and one of its principal vulnerabilities. Yet the program continued to press forward. Manufacturing dispersed. Wichita, Tulsa, Renton, and other plants were retooled. Subcontractors supplied turrets, instruments, and sheet metal. The logistical complexity was staggering. Remote turrets required synchronized fire control systems, analog computers that could calculate lead, the relative motion of incoming fighters, and automatically steer turret guns. The idea was elegant: fewer protruding gun installations, reduced drag, improved range. But significant technical sophistication was required to make those remote systems reliable under combat shock, electrical transients, and battlefield damage. Crew ergonomics, meanwhile, were reconceived. A pressurized cabin made it possible to site a navigator, bombardier, and flight engineer inside a controlled environment. Crews no longer needed to huddle with oxygen masks for every serviceable minute above 20,000 feet. For the long Pacific missions that would later characterize B-29 operations, That mattered. It reduced fatigue, increased mission effectiveness, and permitted longer loiter times over target. But pressurization itself introduced maintenance burdens and failure modes. Leaks had to be found and patched, seals renewed, and structural loads accounted for that would not exist in an unpressurized fuselage. These engineering burdens added weight and complexity. By late 1943, the B-29 was reaching operational squadrons, though not without controversy. Early operational units were plagued by the engine fires, electrical glitches in the remote gun systems, and the difficulty of training entire crews on new, unfamiliar systems. Yet the strategic rationale remained compelling. Bases in India and later in China, part of the complex supply chain known to history as the hump logistics effort, offered the only forward staging areas capable of reaching parts of the Japanese home islands. From these precarious airfields, the B-29 would begin its combat life, often under conditions of shortage and improvisation. Crews flew with an acute awareness that each mission stretched not only the airplane's endurance, but also the limits of supply. The genesis of the Superfortress is, therefore, a story of ambition and trade-off. Designers elected to press forward with innovations, pressurization, remote fire control, massive fuel capacity that promised strategic advantage. Those same innovations complicated the aircraft's reliability and survivability in the earliest operational stages. But the B-29 was not merely the product of engineers' dreams. It reflected a national strategy to build a bomber capable of striking Japan from bases that American forces could secure and hold, to project power across the Pacific, and to make distance less relevant. In the decisions to prioritize range and payload, in the faith placed in cutting-edge engines and remote systems, the B-29 embodied both the technological confidence and the strategic desperation of an America fighting on a global scale. That tension between capability and risk, between visionary engineering and human cost, would define the Superfortress's wartime life. It would carry out missions of unprecedented reach, bring down cities and alter the course of the war, and leave a complex legacy about the price of strategic bombing. But to understand the B-29 fully, one must proceed from the blueprint to the flight line, from calculations on engineers' desks to the test stands where engines were run red hot, to the night training fields where crews learned procedures that would later become matters of life and death. Only then would the promise of the Superfortress and its inevitable perils become entirely visible. The B-29 Superfortress was, in its time, the most advanced bomber ever built, and arguably the most complex single-weapons system produced during World War II. Its designers were not simply building an aircraft, they were building a new philosophy of air warfare. At the heart of that philosophy lay a tension between innovation and reliability, between what could be built and what could survive. Every component of the Superfortress carried that tension inside it, from the remote-controlled gun turrets to the pressurized compartments and the massive Wright R-3350 engines that defined both the aircraft's strength and its fragility. The dream of pressurization. In 1942, few combat aircraft anywhere in the world were pressurized. Commercial aviation had only just begun to experiment with sealed cabins. The Boeing 307 Stratoliner, derived from the B-17, had been the first airliner with full pressurization, and the engineers who built it carried that knowledge straight into the B-29 project. But applying pressurization to a combat bomber introduced challenges that no civilian transport had ever faced. The crew of a B-29 would operate for up to 16 hours at altitudes above 30,000 feet, where outside air pressure was only a third of that at sea level, and temperatures dropped to minus 40 degrees Celsius. In those conditions, unpressurized aircraft forced crews to wear oxygen masks, heavy clothing, and endure freezing, exhausting cold. Pressurization was meant to change all that, to let men move, think, and function as a coordinated team, not as individuals clinging to oxygen lines. The fuselage of the B-29 was therefore divided into three pressurized sections. 1. The forward cabin, housing pilots, bombardier, and navigator. 2. The aft cabin for gunners and radar operators. 3.
the tailgun position, which remained unpressurized. Between the forward and aft cabins stretched a long, unpressurized bomb bay. To connect these compartments, engineers built a pressurized tunnel, a narrow, tubular passage above the bomb racks through which crew could crawl on hands and knees while the aircraft cruised miles above the earth. It was both a triumph of ingenuity and a constant reminder of how radical the design had become. The tunnel made the B-29 look internally like something out of science fiction, part machine, part sealed habitat for men operating at the edge of survivability.
Maintaining that pressurization required a structural revolution. The fuselage skin had to be airtight. Every rivet and seam had to hold against internal pressure differences while the airframe flexed under flight loads. Boeing's engineers developed new techniques for flush riveting, smoother aerodynamic lines, and pressure bulkheads made of reinforced alloys. But this inevitably added weight. Every seal and bulkhead meant additional pounds, and every pound risked range. From the beginning, the B-29 was walking a tightrope between weight and endurance. The Wright R-3350, power and peril. No single component defined the B-29's character more than its engines. The Wright R-3350 duplex Cyclone was a double-row 18-cylinder radial engine, displacing 3,350 cubic inches. At takeoff, each engine produced more than 2,200 horsepower, enormous for its day. Yet this engine, rushed into wartime service, carried unresolved design flaws that would claim hundreds of aircraft and lives before engineers found remedies. Cooling was the first and most dangerous issue. The rear row of cylinders received less airflow than the front, especially under the tight cowling that engineers used to reduce drag. In long climbs or hot tropical conditions, the rear cylinders would overheat. The aluminum heads expanded unevenly, leading to cracks, oil leaks, and, worst of all, engine fires. B-29 crews learned to dread the sight of flames trailing from a nacelle. A fire on one engine could spread to the wing, ignite fuel tanks, and consume the aircraft within seconds. To manage this, ground crews worked constantly, cutting additional air vents, replacing baffling, experimenting with cowl flap settings. Pilots learned new climb procedures, gentler power settings, slower ascents, richer fuel mixtures. Even so, early B-29 groups reported catastrophic losses unrelated to combat. One U.S. Army Air Force's record from the 58th Bombardment Wing noted, more aircraft were lost to engine fire and failure during the initial months of deployment than to enemy interception. The Wright Corporation and the Air Forces formed emergency engineering teams. Modifications included improved cooling fins, better cylinder lubrication, and new fire suppression systems. But the essential trade-off remained. The R-3350 gave the B-29 its extraordinary performance and exacted an extraordinary maintenance burden in return.
Remote-controlled turrets. Precision through complexity. The B-29's remote-controlled gun turrets represented a leap ahead of any other bomber of the era. Instead of each gunner sitting at an exposed position, every turret was operated through an optical sight linked to an analog computer, the Central Fire Control System. This system automatically adjusted for range, bullet drop, target motion, and aircraft attitude. A single gunner could control multiple turrets, and multiple gunners could focus fire on a single target. The effect was revolutionary. It reduced drag by eliminating open blisters and moved the crew safely inside the pressurized fuselage. But the technology required electric servos, gyros, and synchronization that pushed 1940s electronics to their limits. Vibration, battle damage, or electrical faults could disable entire sections of the system. Training gunners to use the new analog sights demanded weeks of simulator work, a concept new to most of the Army Air Forces. The turrets themselves, 4 main remote units plus the tail guns,
gave the B-29 a defensive field of fire that looked formidable on paper. 50 caliber Browning machine guns with interlocking arcs of coverage, some versions even mounting a 20mm cannon in the tail. But the complexity introduced new risks. If the power system failed, turrets froze. If the computing site miscalculated, gunfire could miss entirely. In the heat of combat, when seconds meant survival, the gunner's ability to rely on electronics became both a blessing and a source of tension. Veteran gunner accounts describe this duality vividly. You didn't feel the wind, a vibration of an open gun port, only the sound of servos and the hum of the turret motors. It was like fighting through a machine's nerves. Materials, weight, and production reality. Beyond these high-tech systems lay the oldest constraint of all, materials. Aluminum, steel, and copper were strategic commodities. By 1943, the United States was producing aircraft at rates never imagined before, and even its vast industry faced bottlenecks. The B-29's airframe consumed enormous quantities of duralumin and high-strength alloys. Engineers were forced to make trade-offs: thinner skins in non-critical areas, lighter fittings, and minimal redundancy in hydraulic systems. Every part of the aircraft was an equation: weight versus endurance, strength versus manufacturability. These calculations sometimes bordered on philosophical. How much safety could be sacrificed in pursuit of range?
Factory workers at Wichita, Kansas, one of the primary production centers, remembered the dual mood of pride and fatigue. The B-29 line ran day and night under floodlights. Tens of thousands of rivets per airframe, tolerances tighter than any bomber before it. Inspectors checking every seam because a single leak could compromise the pressurized cabin. Women composed nearly half the workforce, many trained within months to become precision riveters, electricians, or welders. To them, the B-29 was not an abstract concept of strategic bombing. It was tangible labor, metal shaped by hands that rarely saw the sky their creation would cross. Balancing protection and performance. Armor protection in the B-29 reflected another layer of philosophical trade-off. Unlike earlier American bombers, such as the B-17 Flying Fortress, whose nickname celebrated its defensive toughness, the B-29 pursued speed and altitude as its main shields. Only the pilot and co-pilot seats were fully armored. Other crew stations had limited or no armor at all. Self-sealing fuel tanks were included, but the sheer amount of fuel, over 9,500 gallons, meant that a single leak could still ignite devastating fires. Engineers argued that any additional armor would reduce range below the operational requirement for Pacific missions. Thus, the B-29's safety depended less on protection, on performance, on its ability to fly higher and faster than interceptors could reach. This philosophy mirrored the early Japanese reasoning behind the Mitsubishi G4M Betty, though on a vastly more sophisticated level. Where Japan accepted vulnerability for range out of necessity, the U.S. accepted limited armor for strategic geometry. The comparison is haunting. Two nations, separated by ideology and industry, arriving at similar equations of risk. One sought to extend reach through lightness and paid in lives. The other sought to extend reach through complexity and paid in mechanical peril. A machine of paradoxes. The B-29 emerged from these compromises as a paradoxical creation. It was both advanced and fragile, powerful and temperamental. Its design embodied the ambition of a nation that could afford to risk failure in pursuit of superiority. The pressurized cabin, the remote turrets, and the powerful engines were not independent innovations. They were parts of a single system philosophy that technology could offset distance, fatigue, and danger.
In doing so, the Superfortress became a mirror of the industrial United States itself,
a machine built on optimism, scale, and faith that engineering could overcome geography. But like all mirrors, it reflected its flaws. Each new capability introduced new failure points. Every advance came at a cost measured not only in dollars, but in human labor, learning, and, soon enough, in the lives of the men who flew them. By early 1944, the B-29 was no longer a prototype, but a living reality. Hundreds rolled from factories, each carrying within its structure the weight of choices made in drawing rooms and machine shops years earlier. The next stage would test whether those choices could survive contact with war itself. In the skies over India, China, and the Pacific, the Superfortress would prove or disprove the assumptions that had shaped its birth. When the first B-29s left the assembly lines in mid-1943, they represented the culmination of 5 years of design, but also the beginning of a different kind of trial, one not waged against the enemy, but against physics, production pressure, and time. The war would not wait for perfection, and the B-29 had to prove itself in the harshest possible classroom: combat readiness under wartime urgency, baptism by fire and malfunction. Even before it ever faced Japanese anti-aircraft guns, the B-29 faced its first and most relentless enemy, itself. The Wright R-3350 engines, which engineers had warned were delicate thoroughbreds, began to show their volatility when placed under continuous operational stress. Pilots from the 58th Bomb Wing training in Kansas and later in India reported an unnerving pattern. One engine after another would burst into flames mid-flight. Crews developed rituals to cope: constant checks of oil pressure, feathering props at the first sign of rising temperature, memorizing bailout procedures. A few jokes circulated, bitter ones: if you see fire on your right wing, turn left and pray. But behind the dark humor was genuine fear. In June 1943, Colonel Harmon's test flight from Boeing Field ended in disaster when an engine fire spread to the fuel system. The aircraft, prototype number 41-0003, disintegrated in midair, killing all aboard, including key engineers from Boeing and Wright. The incident was a national secret, but among the engineers and pilots, it became a grim symbol of what they were dealing with. An internal report summarized the danger with understated precision. Fire suppression systems are inadequate for wing structure of this size. Ignition of main tanks is unrecoverable. Still, there was no turning back. The B-29 project consumed nearly $3 billion, an astronomical sum in 1940s dollars, more than the Manhattan Project that was developing the atomic bomb. To cancel it was politically impossible. To slow it was militarily unthinkable. Thus, the aircraft entered war zones before it was truly mature, a decision made not out of negligence, but out of necessity.
Operation Matterhorn, flying from the edge of the world. The first B-29 operations under Operation Matterhorn were based not in the Pacific Islands, but in the remote airfields of India and China. The plan was audacious: launch bombers from India, fly over the Himalayas, the hump, refuel and rearm in western China, then strike Japan from those Chinese bases. It was an engineering and logistical nightmare disguised as a strategy. Everything, fuel, bombs, spare parts, had to be flown over the Himalayas by the same bombers that would later bomb Japan. A single B-29 mission to Japan could consume more fuel than it carried to China, meaning it often took 6 shuttle flights to prepare for one bombing run. Mechanics worked in primitive conditions: mud, heat, and monsoon rains, often under Japanese air raids. Engines overheated in the tropical humidity, landing strips melted in the sun, and dust clogged filters. The Wright R-3350, already temperamental, reacted badly to India's heat. Oil pressure dropped, engines detonated, fires became routine. A technical officer at Kharagpur recorded in his log, "We lost 3 of 8 aircraft aborted takeoff due to overheating. One lost 2 engines en route and ditched near the coast. Crew survived. Plane lost. We call it mechanical attrition." Even when aircraft reached their staging bases in China,
Supplies were scarce. Crews slept in bamboo huts, eating rice and powdered eggs, surrounded by local villagers who watched the machines of the industrial age thunder across their rice paddies. It was as if 2 centuries, agrarian and mechanical, collided in one valley. The B-29s that finally reached Japan often did so with reduced bomb loads, limited fuel reserves, and exhausted crews. Bombs fell wide. Missions were scattered. Weather and inexperience claimed more aircraft than enemy action. Still, it was history's first bombing of Japan since the Doolittle raid of 1942, and Washington celebrated it as a strategic victory. But within the bomber crews, there was no triumph, only exhaustion and doubt. A navigator recalled years later, "It felt less like striking the enemy and more like testing whether our own machines could even get there and back."
The weight of complexity. Every B-29 required 60,000 man-hours to build, and nearly as many to keep in the air. At forward bases, maintenance crews worked 12-hour shifts around the clock, often cannibalizing parts from damaged aircraft to keep others flying. When a B-29 returned from a mission, it was not just refueled, it was practically rebuilt. A single broken cooling fin could mean catastrophic engine failure. A malfunction in the pressurization system could leave the crew hypoxic over enemy territory. Technicians nicknamed the bomber 1,000 systems waiting to fail. This level of complexity had one advantage. It forced an unprecedented collaboration between engineers and airmen. Wright Corporation sent specialists to India. Boeing dispatched field teams. Even the U.S. Navy contributed metallurgical research to solve cracking issues in engine cylinders. But the lesson was clear. The age of the pilot as master of a simple machine was over. Now the machine dictated the limits. The crew became custodians of a technological organism that demanded ritual care and obedience. In some ways, the B-29 was less a weapon than an ecosystem. Fragile, interdependent, and merciless to error. Fire on the ground. If the engines could burn in flight, they could also burn on the ground. Maintenance hangars became scenes of disaster when fuel lines ruptured during testing. At least 12 B-29s were destroyed in ground fires before they ever flew a mission. The Army Air Forces instituted emergency protocols, fire trucks positioned around every runway, crews trained to evacuate in seconds, but the aircraft's sheer mass made it difficult to handle. Fully loaded, a B-29 weighed over 140,000 pounds, the heaviest bomber of its time. Brakes overheated, tires burst, and runways cracked under the stress. In India, mechanics developed the term elephant walk to describe the massive, ponderous takeoff sequence of multiple bombers rolling simultaneously. A visual metaphor for their vulnerability. Each one was a potential inferno, its engines trembling at redline RPM, hoping to lift before a spark turned aluminum and fuel into flame. Human cost. Statistics from the early B-29 operations are staggering. Between 1943 and mid-1944, the U.S. Army Air Forces lost nearly 400 aircraft to non-combat causes. Training accidents, mechanical failures, and fires. Hundreds of crewmen died before ever seeing an enemy interceptor. In one training mission out of Pratt, Kansas, 2 aircraft collided in formation due to turbulence. Both exploded, scattering debris across the prairie. In another, a pilot attempted to nurse a burning B-29 back to base, but exploded on final approach. All 11 aboard perished. The losses forced the Air Forces to rethink their doctrine. Where early publicity had called the Superfortress a fortress in the sky, the men flying it began calling it a flying furnace. Yet even amid fear, morale did not collapse. Crewmen wrote home about the danger with a fatalistic pride, not bravado, but a quiet recognition that they were part of something larger than themselves. Learning to live with the beast. By late 1944, modifications began to pay off. Improved engine baffles, better lubricants, and procedural discipline reduced fire incidents. Crews learned to nurse their engines, climb slowly, lean mixtures carefully, use cowl flaps strategically. In effect, every pilot became a part-time engineer. Flight engineers, a new position introduced with the B-29, gained authority nearly equal to the pilots. They monitored gauges, temperatures, pressures, keeping the engines alive through intuition as much as training. A veteran recalled, "You didn't just fly a B-29, you negotiated with it. You listened for its moods." That statement, half poetic and half mechanical, captured the soul of the aircraft. The B-29 was a masterpiece that demanded humility from those who touched it. It was a triumph of engineering that punished arrogance. Gradually, squadrons began to master their machines. Mechanics found patterns. Pilots trusted procedures. Gunners trained on simulators until the remote turrets became extensions of instinct. Out of chaos, a new professionalism emerged, one defined not by glory, but by endurance. The transition to the Pacific. By late 1944, the U.S. had secured the Mariana Islands, Saipan, Tinian, and Guam, which placed Japan itself within direct striking range. This would change everything. The Matterhorn operation in China was quietly phased out. The Pacific bases offered shorter routes, better logistics, and safer staging. But before the aircraft could make history in the Marianas, it had to survive its own creation, a trial by mechanical fire and human perseverance. Every burned engine, every failed flight, every crash prototype became a lesson written in blood and aluminum. In those lessons, the B-29 transformed from a flawed miracle into a reliable machine. And behind that transformation lay something deeper, the recognition that technology alone could not conquer nature. It had to be learned, lived with, and, in a strange way, respected.
The crews who survived those early months would later say that by the time the B-29 reached the Pacific, they no longer feared it, they understood it. And that understanding, born of frustration, loss, and adaptation, would soon unleash one of the most devastating bombing campaigns in history. By mid-1944, the B-29 Superfortress had survived its own infancy, proving that its engines could be managed, its systems maintained, and its enormous weight lifted reliably from runways across India and China. But survival in training was one thing. Survival in combat over the Pacific was an entirely different calculus. The capture of the Mariana Islands, Saipan, Tinian, and Guam, offered the United States something previously unattainable, a forward base within range of the Japanese home islands that could support fully loaded B-29s without requiring the logistical gymnastics of Operation Matterhorn. The strategic calculus. From the outset, American planners recognized the B-29 as a weapon not merely of destruction, but of psychological and industrial leverage. Strategic bombing theory, shaped by doctrines developed in Europe and by American industrialist military thinkers, envisioned the B-29 as the instrument capable of crippling Japanese production while eroding civilian morale. Colonel Haywood Hansell, commander of the 21st Bomber Command, advocated precision daylight bombing, modeled on lessons from the RAF and the U.S. 8th Air Force in Europe. The theory was simple. If the Superfortress could fly high and fast, with its defensive armament covering multiple arcs, it could strike industrial targets and return with acceptable crew losses. Yet the Pacific presented unique variables. Weather, jet streams, and typhoons over vast distances complicated calculations. Early B-29 missions over Tokyo in November 1944 demonstrated these difficulties vividly. Crews discovered that even at 30,000 feet, wind currents could displace bombs by miles. Cloud cover obscured targets. Temperatures at altitude caused systems to malfunction. Bombers carried 10,000 pounds of bombs, but accuracy was often worse than random chance.
A navigator on the first Tokyo mission recorded, "The city is beneath us, yet elusive. We release and hope for impact. Machines obey physics, not human intention." The lesson was clear. Technology offered range and payload, but nature dictated results. The first combat missions. The first combat sorties from Saipan and Tinian in November 1944 were baptism by fire. But unlike India, crews now faced a concentrated enemy. Japanese air defenses, though weakened, still included fighters and anti-aircraft artillery capable of threatening high-altitude formations.
The B-29's defensive armament, 10 50 caliber M2 Browning machine guns and 4 remote-controlled gun turrets, seemed formidable on paper. In practice, coordination between gunners, visibility limits, and mechanical failures frequently reduced effectiveness. Turrets jammed, gunners misidentified targets, remote sights failed in clouds or haze. Even when fully operational, defensive fire could not cover every approach vector. Japanese flak, concentrated around industrial centers and urban zones, forced crews to fly erratically, sometimes dropping below ideal bombing altitudes. Losses were inevitable. In the first 3 missions over Tokyo, 6 bombers were lost, 44 crewmen killed or missing. Others returned damaged, engines smoking, hydraulic lines punctured, fuselage dented by high-explosive shells. Despite the challenges, American command analyzed each sortie with obsessive precision. Post-mission debriefs examined engine performance, defensive fire accuracy, altitude drift, fuel consumption, and bomb pattern dispersion. Every failure produced a new protocol: engine cooling procedures, gunnery retraining, formation spacing adjustments. In effect, the B-29s were teaching crews how to fight in ways the designers could never have anticipated. Curtis LeMay and the shift to firebombing. By early 1945, it became evident that precision daylight bombing was not yielding strategic results. Urban dispersal, camouflage, and Japanese industrial decentralization minimized the effect of high-altitude raids. Losses continued, and the cost in crews and aircraft was growing unsustainable. Enter General Curtis LeMay, a man whose philosophy would transform both the B-29 and the very nature of warfare in the Pacific. LeMay proposed a radical change: abandon high-altitude precision for low-altitude incendiary raids. The B-29, previously imagined as a fortress in the sky capable of exact strikes, was to become a tool of fire and terror. Wooden cities, densely packed, provided combustible material ideally suited for incendiary attack. The new strategy was simple in concept, brutal in execution. Fly low, drop firebombs, and overwhelm both target and defenses. The first major firebombing raid on Tokyo occurred on March 9th and 10th, 1945. 334 B-29s carried a payload of 1,665 tons of incendiaries. Flying at altitudes between 5,000 and 9,000 feet, crews released M69 bomblets designed to ignite upon impact, creating a firestorm. The results were catastrophic for the city and devastatingly effective for strategic aims. Over 100,000 civilians died. Large areas of Tokyo were destroyed. Aircraft losses were relatively low, confirming LeMay's calculation. Altitude reduction minimized fuel consumption, mechanical strain on engines, and exposure to flak.
Technology meets morality. This shift in tactics raised uncomfortable philosophical questions. The B-29, originally conceived as a precision weapon, had become an instrument of total war, where the distinction between military and civilian blurred. The aircraft's performance characteristic, payload, range, and speed, enabled unprecedented destruction, but they also forced planners and crews to confront the ethical implications of their use. Pilots reported mixed feelings. One veteran wrote in his diary, "We flew machines of metal and fire. They did what we commanded, but in the streets below,
There were no enemies in uniform, only a city consumed. The B-29 thus embodied a duality, a marvel of engineering, yet a vessel of moral ambiguity. Its capabilities allowed the United States to project power across thousands of kilometers. But that same capability required accepting civilian casualties as a tactical reality, adaptation and industrial resilience. Meanwhile, the B-29's logistical and engineering challenges continued. Engines still overheated, landing gear still failed, and turrets still jammed. LeMay's operational tempo exacerbated wear. Planes flew nightly missions, often returning to Saipan with mechanical failures that would have grounded earlier aircraft indefinitely. Yet American industrial capacity and field engineering allowed rapid repair cycles. Crews became adept at improvisation, replacing engines in the field, cannibalizing spare parts, and adjusting flight plans to accommodate mechanical limitations. In this sense, the B-29 campaign demonstrated a critical principle. Technology alone does not win wars. Technology integrated with industrial capacity, tactical innovation, and human adaptability creates strategic leverage. Lessons learned. By mid-1945, the consequences of the B-29 campaign were visible. Japan's urban infrastructure was devastated, industrial production crippled, and civilian morale shattered. Losses of aircraft and crews, though lower than initially feared, were still significant, highlighting the human cost of long-range strategic bombing. The B-29 story illustrates several enduring truths. 1. Design versus doctrine. The aircraft's engineering enabled unprecedented range and payload, but operational doctrine required continual adaptation. An airframe optimized for high-altitude precision became a platform for low-altitude firebombing, a testament to flexibility in applying technology. 2. Performance versus survivability. Engines prone to failure required human adaptation and industrial support to maintain operational effectiveness. The Superfortress was powerful, but its full potential depended on infrastructure and discipline as much as design. 3. Ethics and technology. As the instrument of strategic bombing, the B-29 forced a confrontation between technological capability and moral responsibility. Its performance was unmatched, but its use blurred lines between combatant and non-combatant, raising questions about the human consequences of technological superiority.
Ultimately, the B-29's role in the Pacific War was as much about shaping strategy and psychology as about destroying targets. It bridged continents, carried the weight of American industrial might, and forced both planners and crews to reconsider the limits of warfare. In the coming months, the B-29 would deliver atomic payloads over Hiroshima and Nagasaki, cementing its legacy as a machine of both extraordinary technical achievement and profound ethical consequence. But before that final chapter, the aircraft had first survived its own infancy, proved its combat worth, and reshaped the very concept of aerial warfare. The B-29 Superfortress, having survived its baptism of fire over Tokyo, had by mid-1945 become the centerpiece of American strategic air power in the Pacific. Its performance metrics, range, payload, speed, and altitude were unmatched in any theater, providing the United States with a platform capable of delivering weapons beyond the reach of any other nation. Yet, with the introduction of atomic ordnance, the B-29's significance transcended conventional bombing. It became the instrument through which the future of warfare would be irrevocably altered. Technological adaptation. Preparing for the atomic mission. The atomic bomb presented a set of unprecedented engineering challenges. The standard B-29 configuration could not accommodate the size, weight,
and environmental requirements of the Little Boy and Fat Man bombs. Specialized modifications were essential, resulting in the Silver Plate program, a comprehensive redesign of aircraft systems to optimize them for atomic delivery while preserving operational reliability. Modifications included removal of gun turrets to reduce weight, reinforcing bomb bays with titanium and aluminum structures to support ordnance weight, and recalibrating engines for extended maximum output. Electrical and hydraulic systems were re-engineered to handle the demands of the bomb release mechanisms, and environmental controls were upgraded to prevent temperature fluctuations from affecting the fissile material. The result was a B-29 that sacrificed defensive capability for strategic capability. Unlike the Betty bomber, which had been designed for range and speed at the expense of crew survival, the Silver Plate B-29s deliberately reduced defensive armament to accommodate payload and altitude performance, relying on planning, surprise, and operational support rather than structural invulnerability. The aircraft chosen for atomic delivery, Enola Gay and Boxcar, were subjected to rigorous test flights and simulations. Engineers and pilots meticulously calculated release trajectories, altitude profiles, and timing to ensure both mission success and crew safety. The precision required far exceeded any previous mission. Atomic ordnance was unforgiving, both in detonation mechanics and political consequences.
Hiroshima, the calculus of devastation. On August 6, 1945, the Enola Gay, piloted by Colonel Paul W. Tibbets, lifted from Tinian at 0245 local time. The crew carried a 9,700-pound Little Boy bomb, designed to release its energy through nuclear fission and create a destructive radius unprecedented in human history. The mission required precision, timing, and navigation at a level previously untested. Target selection involved not only industrial and military value, but also population density, city layout, and wind patterns. Japanese air defenses, though largely degraded, were still a consideration. Flak and potential fighter interception had to be calculated. The B-29, stripped of most defensive armament, relied entirely on altitude, speed, and surprise for survival. Its previous missions over Japan had prepared crews to understand the risks of exposure. Unarmored sections could be destroyed by flak, engines could fail under sustained power, and mechanical anomalies could compromise the release. In this sense, the atomic mission represented the ultimate fusion of engineering precision and human calculation. At 0815 local time, over Hiroshima, the bomb was released. Within seconds, the city was engulfed in a blinding flash, followed by a massive fireball and subsequent firestorm. The destruction of industrial infrastructure and civilian areas was immediate and total. Estimates suggest over 70,000 individuals perished instantly, with total casualties by the end of 1945 exceeding 140,000. From a technical standpoint, the B-29 performed flawlessly. Its altitude, speed, and release mechanism ensured that the bomb detonated at the calculated airburst height of 1,900 feet, maximizing blast radius and thermal effects while minimizing crew exposure to radioactive fallout. Yet the mission, while a technical triumph, raised profound ethical questions. The aircraft's capability enabled destruction on a scale unimaginable in prior conflicts, but at a human cost that challenged the moral calculus of war. Nagasaki and operational lessons. 3 days later, on August 9th, the Boxcar, piloted by Major Charles W. Sweeney, delivered Fat Man over Nagasaki. The mission highlighted both the strengths and limitations of the B-29 platform. Weather complications forced multiple course corrections, demonstrating the necessity of advanced navigation, communication, and decision-making. Fuel calculations were critical. The B-29's operational range was tested to near limits, requiring precise management to ensure return to base. The bomb, heavier and differently configured than Little Boy, required adjusted release procedures and altered flight profiles. The B-29's airframe, designed for flexibility, accommodated these changes without structural failure. Yet the operation also revealed the fragility of the mission. A single miscalculation in altitude, speed, or timing could have resulted in failure or catastrophic loss of the aircraft and crew.
Comparison with the Betty bomber philosophy. When juxtaposed with the Japanese G4M Betty, the B-29 represents a divergent philosophy of aircraft design and operational doctrine. Both aircraft were produced to project power over vast distances and carry significant ordnance. Both faced operational risks inherent to their theaters. Yet the guiding principles diverged. 1. Crew survival versus mission primacy. The B-29, particularly the silver plate variant, balanced mission effectiveness with survivability through planning, altitude, and industrial support, rather than structural vulnerabilities. The Betty prioritized range and payload at the expense of crew survival, accepting catastrophic losses as a design consequence. 2. Adaptability and industrial integration. American engineering emphasized repair, redundancy, and operational support. Crews trained to mitigate mechanical failures and environmental hazards. Japanese engineering accepted fragility as a trade-off for performance metrics. 3. Strategic ethics embedded in design. The B-29's use of atomic ordnance forced explicit ethical decisions at the highest levels, integrating human cost into mission planning. The Betty's design indirectly imposed mortality through structural decisions, leaving crews vulnerable without choice. The philosophical implications are profound. Aircraft are not merely machines. They are embodiments of national priorities, industrial philosophy, and ethical frameworks. The B-29 and the Betty serve as case studies in how technology, doctrine, and human life intersect in warfare. One prioritized minimizing crew risk while maximizing mission success. The other accepted near-certain casualties to achieve operational reach. Both achieved their goals, but with drastically different consequences for those who flew them.
Ultimately, the B-29's atomic missions stand as a historical mirror to the Betty bomber's Pacific career. Both were instruments of power, both relied on extreme engineering solutions, and both forced reassessment of the relationship between technology and human life. The difference lies in intentionality. The B-29's success relied on deliberate balancing of capability and crew survival, while the Betty's lethality was a product of design choices that treated crews as expendable by design. The conclusion of World War II did not end the story of the B-29 Superfortress. Rather, it transformed the aircraft from a tool of war into a lens through which the interplay of technology, strategy, and human cost could be studied. Its operational history, from the skies over Japan to post-war occupation duties, offers a rich case study in how engineering choices, doctrine, and ethics intersect. Transition to peacetime and occupation roles. Following Japan's surrender in August 1945, B-29s were repurposed for occupation, reconnaissance, and repatriation missions. These operations highlighted the aircraft's versatility. Its long range and payload capacity allowed it to transport supplies to remote locations and conduct photographic mapping of previously inaccessible regions. The transition demonstrated a fundamental principle. Aircraft are not defined solely by their original wartime purpose, but also by the operational environment and the strategic requirements imposed by human planners. Yet even in peacetime, the moral and technical lessons of the B-29's atomic missions remained inescapable. Crews were acutely aware of the destruction they had wrought. The aircraft, designed to carry the heaviest payloads over the longest distances, had transformed theoretical engineering calculations into tangible consequences for human populations. The psychological imprint on pilots and support personnel was profound, a reminder that operational success is inseparable from ethical responsibility. Comparative analysis with the Betty bomber. When juxtaposed with the Japanese G4M,
the post-war analysis underscores fundamental differences in philosophy and outcomes. Both aircraft were designed to project national power across vast distances, yet the resulting human cost diverged sharply. 1. Crew survivability. B-29. Structural integrity, defensive modifications, and operational planning emphasized crew survival. Even during atomic missions, extensive simulations and rehearsals reduced the probability of accidental loss. G4M prioritized range and payload over structural protection. Crews faced near-certain mortality in contested airspace, a reflection of design decisions made under restrictive performance requirements and flawed assumptions about enemy capabilities. 2. Strategic flexibility. B-29. Adaptable to conventional bombing, atomic delivery, reconnaissance, and occupation support. Its design enabled multiple mission profiles without requiring fundamental redesign. G4M. Optimized for long-range strikes but lacked flexibility. Modifications for increased protection compromised performance, demonstrating the difficulty of balancing competing design priorities. 3. Philosophical implications. B-29. Operational doctrine and engineering philosophy reflected a holistic approach. Technological capability was integrated with crew safety and ethical considerations. G4M. Engineering decisions revealed a doctrinal willingness to accept catastrophic casualties in pursuit of performance, highlighting cultural and strategic differences in valuing human life during conflict.
Industrial and technological lessons. The B-29 also provides insight into the broader role of industrial capacity in determining wartime outcomes. American factories, with unprecedented scale and efficiency, enabled mass production of highly complex aircraft. This industrial power allowed continuous innovation, from initial bombing missions over Japan to the Silver Plate atomic modifications. Redundancy, quality control, and supply chain management ensured that aircraft returned from missions could be repaired and returned to service with minimal delay. In contrast, Japanese industrial constraints limited the potential for iterative improvement in aircraft design. The G4M's initial vulnerabilities could not be fully corrected due to material shortages, Allied bombing of production facilities, and limitations in engineering manpower. Even the introduction of the G4M Model 3 with self-sealing fuel tanks arrived too late and in insufficient numbers to alter the strategic calculus. The lesson is clear. Engineering decisions cannot be isolated from industrial and logistical realities. A technically brilliant aircraft can be rendered strategically ineffective if production capacity, material availability, or operational support is insufficient. Ethical reflections and the value of human life. Perhaps the most profound legacy of the B-29 lies in the ethical dimension of aircraft design and deployment. The atomic missions demonstrated that technological capability carries an inherent moral responsibility. Engineers, planners, and pilots were confronted with questions that extended beyond performance metrics. How much destruction is justified by strategic objectives? What safeguards are required to protect non-combatants and crews alike? The contrast with the G4M highlights how differing cultural and strategic assumptions shape these answers. Japanese designers assumed that high crew casualties were an acceptable cost of achieving operational goals. American designers, while prioritizing destructive capability, also invested in crew protection, reflecting a philosophy that human life could not be entirely subordinated to mission requirements. In both cases, the aircraft became a mirror of national priorities. The B-29 embodied a balance between capability and survivability, demonstrating that operational success need not come at the total expense of human life. The G4M embodied a willingness to sacrifice crews for performance, revealing how doctrinal imperatives can translate into catastrophic human cost. Strategic doctrine and the future of aviation. Post-war, the lessons of the B-29 influenced both doctrine and technology. The concept of strategic bombing, atomic deterrence, and long-range operational reach shaped the U.S. Air Force's approach to the Cold War. Aircraft were designed not only for performance, but for sustainability.
crews had to survive missions to preserve operational continuity and strategic flexibility. In design philosophy, engineers began to integrate survivability as a core requirement rather than a trade-off. Advances in materials, redundancy, and defensive systems reflected a recognition that human operators are irreplaceable assets in a technological system. The B-29's history provided empirical data to support these decisions, proving that balancing performance with protection enhances long-term strategic effectiveness.
Conclusion: the philosophical legacy of the B-29. The B-29 Superfortress serves as more than a historical artifact. It is a case study in the intersection of technology, strategy, and ethics. Its operational history, from conventional bombing campaigns to atomic missions, illustrates the consequences of engineering decisions in a complex wartime environment. When compared to the Japanese G4M, the contrast is stark. Capability without consideration for human survival results in high attrition and strategic fragility, while careful integration of protection, operational planning, and industrial capacity maximizes effectiveness and preserves human resources. Ultimately, the B-29's legacy is a reminder that engineering choices are never neutral. They encode values, reflect priorities, and determine outcomes for both machines and the humans who operate them. The Superfortress demonstrated that technological power, when combined with foresight and ethical consideration, can shape history without unnecessarily sacrificing those who wield it. In the annals of military aviation, the B-29 stands as a monument to deliberate design, strategic insight, and the complex calculus of human life in warfare. Its story, juxtaposed with the G4M, provides lessons that extend far beyond World War II, offering enduring guidance for engineers, strategists, and policymakers faced with the consequences of technological power. The study of the B-29 Superfortress alongside the Japanese G4M Betty bomber is more than a historical exercise. It provides enduring lessons in engineering, operational doctrine, strategic planning, and ethical responsibility. While separated by geography, culture, and industrial capacity, these aircraft embodied two radically different approaches to aerial warfare, with consequences that extend far beyond the battlefields of the Pacific. Engineering philosophy and design trade-offs. At the core of the comparison lies a fundamental question. How should aircraft be designed to balance capability and survivability? 1. The B-29 Superfortress. Design emphasized integration of advanced technology with crew protection. High-powered engines, pressurized cabins, defensive armament, and redundancy were balanced with payload capacity and range. Extensive use of armor plating, self-sealing fuel tanks, and defensive turrets reduced vulnerability. Weight penalties were accepted because the industrial base allowed mass production and innovation without compromising operational capacity. 2. G4M Betty bomber. Design prioritized range and speed over survivability, reflecting Japanese Navy specifications. Fuel tanks were unprotected. Armor was minimal. Even minor hits could result in catastrophic fires. Design philosophy assumed limited enemy interference and short conflict duration, assumptions that quickly proved fatal once sustained combat commenced.
The technical contrast demonstrates that aircraft design is inseparable from both operational assumptions and the resources available to support those assumptions. Japanese engineers made deliberate choices, fully aware of the risks, to achieve extraordinary range. American engineers designed for sustainable operational success, accepting weight penalties and complexity to preserve human life. Operational outcomes. The operational histories of these aircraft illustrate the consequences of their respective design philosophies. B-29 enabled sustained strategic bombing, including atomic missions, with relatively low attrition rates for crews compared to mission scale. Flexibility allowed adaptation to multiple roles,
including reconnaissance, occupation support, and transportation. G4M. Initially a formidable weapon, the bomber quickly became a liability as American fighter strength grew. By 1943, missions often became effectively suicidal, with thousands of Japanese aircrew lost in operations where survival depended on chance. The contrast reinforces that technological capability is only meaningful when paired with operational feasibility and human survivability. Performance metrics like speed, range, or payload cannot compensate for vulnerabilities that ensure near-certain attrition. Strategic and industrial implications. The B-29's success was inseparable from the American industrial machine. Mass production, standardization, and supply chain efficiency allowed continuous improvements without compromising operational availability. Japanese industry, constrained by material shortages and Allied bombing, lacked the capacity to correct the G4M's vulnerabilities at scale. This comparison highlights an enduring principle. Strategic outcomes depend not only on technical design, but also on industrial capacity, logistical support, and adaptability. Even a technically brilliant aircraft can fail if the broader system cannot sustain its operation. Ethical considerations and human cost. Beyond technical and operational analysis, these aircraft tell a story about the value of human life in military strategy. B-29 crews operated within a framework that valued survival alongside mission accomplishment. Protective design features, training, and operational planning mitigated unnecessary risk. G4M crews were subject to design decisions that effectively treated human life as expendable in pursuit of mission objectives. Survival depended less on skill or bravery and more on luck.
This dichotomy illuminates how engineering decisions are deeply ethical acts. Choices about armor, fuel protection, redundancy, and operational doctrine directly determine whether operators live or die. The B-29 embodies a philosophy that human life is integral to operational effectiveness. The G4M reflects a philosophy where mission accomplishment can justify catastrophic attrition. Lessons for modern aviation. Modern aircraft design continues to reflect the tension between performance and survivability. Stealth aircraft, unmanned systems, and hypersonic weapons all involve trade-offs between operational capability and human or material risk. The historical comparison of B-29 and G4M offers several lessons. 1. Integration of technology and ethics. Designers must account for the survivability of crews and operators as a critical performance metric. 2. Operational assumptions. Aircraft must be designed with realistic assumptions about enemy capabilities, duration of engagement, and mission conditions. 3. Industrial support. Even the most advanced aircraft cannot succeed without an industrial base capable of sustaining production, maintenance, and upgrades. 4. Flexibility and adaptability. Multi-role capability and adaptability to changing operational contexts increase strategic value. Philosophical reflection. The B-29 and G4M narratives converge on a single profound insight. Technology is never neutral. Each aircraft embodies a set of values, assumptions, and priorities. The B-29 demonstrates that maximizing capability while protecting human life yields sustainable, effective power projection. The G4M demonstrates that performance pursued at the expense of survivability can result in tactical success but strategic vulnerability, culminating in catastrophic human loss. The ethical dimension is inseparable from technical and strategic considerations. In essence, the story of these aircraft is also the story of how societies value human life in the calculus of warfare. Conclusion. In conclusion, the comparative study of the B-29 and G4M offers lessons that extend far beyond the Pacific War. Engineering and operational decisions must be analyzed holistically, considering capability, survivability, industrial capacity, and human cost. Sustainable military power is achieved not only through technological superiority,
but through the protection of human operators and the capacity to endure prolonged conflict. The consequences of prioritizing performance over survivability are immediate and measurable, both in human casualties and long-term strategic effectiveness. The legacy of these aircraft continues to inform modern aviation, military doctrine, and ethical reflection. Their histories remind us that every design decision is a moral decision, every mission plan a philosophical statement, and every technical innovation is a question about the value of human life in the pursuit of national objectives. In the final analysis, the B-29 and G4M are more than war machines. They are mirrors reflecting the philosophies, capabilities, and ethical frameworks of the nations that built them. And their stories continue to teach lessons about the complex interplay of technology, strategy, and humanity that remain relevant in every era of conflict. Era of conflict. Era of conflict. Era of conflict.